Hello! In this video, we are going to prove the following theorem. Let a and b be real numbers, where a is greater than b is greater than 0. And let j and k be integers, where j is greater than or equal to 0 and k is greater than or equal to 1. Then, a to the power of j times b to the power of k is less than a to the power of j plus k. Okay, now before we get to the proof, we are going to use the following fact in our proof. Given any two positive real numbers r1 and r2, if r1 is less than r2, then for all positive integers n, r1 to the power of m is less than r2 to the power of m. Okay, so now let's get into the proof. Now, let's start out by giving ourselves two real numbers, a and b, where a is greater than b is greater than 0, and let's give ourselves an integer k that is greater than or equal to 1. From here, we are going to show that for all integers j greater than or equal to 0, we have that this is true. And we're going to show that by induction. So let's start with the base case. Now in the base case, we're trying to show that this is true in the case where j is equal to 0. Which means we're trying to show that a to the power of 0 times b to the power of k is less than a to the power of 0 plus k. So this is what we're trying to prove. And let's start out by writing the left-hand side. Now we know that any real number to the power of 0 is just 1. So really this is just equal to b to the power of k. But now we can apply this fact, right? Because if we take r1 and r2 to be b and a respectively, we have that if b is less than a, then this is true. Well, b is less than a, so this is true. Which means we have that for all positive integers n, b to the power of m is less than a to the power of m. So if we take m to be k, then we have that b to the power of k is less than a to the power of k. And we know that a to the power of k is the same thing as a to the power of 0 plus k. So as you can see, we have shown that this is less than this, which is what we wanted to show. So this completes the base case. Now let's move on to the induction step. Now in the induction step, we give ourselves an arbitrary integer j greater than or equal to 0, where this holds. And the whole goal now is to show that this is also true for j plus 1. So this is what we're trying to prove now. And let's start out by writing the left-hand side. Now, we know that a to the power of j plus 1 is equal to a to the power of j times a. But then, if we take this inequality and multiply the positive number a on both sides, we get that a to the power of j times b to the power of k is less than a to the power of j plus k times a. But then, of course, this is the same thing as a to the power of j plus k plus 1. So as you can see, we have shown that this is less than this, which is exactly what we wanted to show. So this completes the induction step. And because we've completed both the base case and the induction step, this closes the induction, which means we have shown that for all integers j greater than or equal to 0, this is true. So now let's put this all together. Since a and b were arbitrary real numbers where a is greater than b is greater than 0, and k was an arbitrary integer where k is greater than or equal to 1, we have that for all real numbers a and b where a is greater than b is greater than 0, and all integers k where k is greater than or equal to 1, it follows that for all integers j greater than or equal to 0, we have that this is true. And that's exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.